In the last section, you learned that random variables can be classified as either discrete or continuous. In most instances, the value of a discrete random variable is determined by counting. Several theoretical discrete distributions have extensive application in business decision making. A probability distribution is called theoretical when the mathematical properties of its random variable are used to produce its probabilities. Such distributions are different from the distributions that are obtained subjectively or from observation. This section and the next focus on theoretical discrete probability distributions. The first theoretical probability distribution we will consider is the binomial distribution that describes a process whose trials have only two possible outcomes. The physical events described by this type of process are widespread. For instance, a quality control system in a manufacturing plant labels each tested item as either defective or acceptable. A firm bidding for a contract either will or will not get the contract. A marketing research firm may receive responses to a questionnaire in the form of yes, I will buy, or no, I will not buy. The personnel manager in an organization is faced with two possible outcomes each time he offers a job. Applicant either accepts the offer or rejects it. An effective method for counting the number of ways binomial events can occur is called the counting rule for combinations. This rule is used to find the number of outcomes for an experiment in which X objects are to be selected from the group of N objects. The key to developing the probability distribution for a binomial process is to first determine the probability of any one way the event of interest can occur, and then to multiply this probability by the number of ways that can occur. We can simplify a few steps by using the binomial formula. This formula is composed of two parts, the combination of X items selected from N items and the probability that X items can occur. For example, let's say 35% of all voters support Proposition A. If a random sample of 10 voters is polled, what is the probability that exactly 3 of them support the proposition? Here we are looking for X equal to 3, N equal to 10, and P equal to 0.35. Plugging in the values into the binomial formula results in 25.22% chance that exactly 3 out of 10 voters will support Proposition A. Using the binomial formula to develop the binomial distribution is not difficult, but it can be time-consuming. To make binomial probabilities easier to find, you can use the binomial table in Appendix B. This table is constructed to give cumulative probabilities for different sample sizes and probabilities of success. Each column is headed by a probability P, which is the probability associated with a success. The column headings correspond to probabilities of success ranging from 0.01 to 1.00. Down the left side of the table are integer values that correspond to the number of successes, x, for the specified sample size, n. The values in the body of the table are cumulative probabilities of x, or fewer, successes in a random sample size of n. Referring to previous example, you can see how the table makes this process quicker to achieve the same result. The equation for the expected value can be used with any discrete probability distribution, including the binomial. However, if we are working with the binomial distribution, the expected value can be found more easily. Likewise, if a discrete probability distribution meets the binomial distribution conditions, the standard deviation can be more easily computed. At this point, several comments about the binomial distribution are worth making. If P, the probability of success, is 0.50, the binomial distribution is symmetrical and bell-shaped, regardless of the sample size. When the value of P differs from 0.50 in either direction, binomial distribution is skewed. The skewness will be most pronounced when n is small and P approaches 0 or 1. However, the binomial distribution becomes more bell-shaped as n increases. Go ahead and open Excel file shoe size and answer the following questions. I've begun this problem by setting up a column that will determine if the shoe was returned. I'll do this by using an if function. If columns A and B are equal, it will return a no, and if not, it will return a yes. Now go ahead and insert a pivot table and determine the frequency of returns. As you can see, I've set mine up so I have returned in columns, showing the number of returns and the percent of returns. Now we also want to calculate the probability of obtaining at least that many pairs of wrong size shoes delivered to customers if the proportion of incorrect sizes is actually 0.05. So in this case, n is 125 and our p would be 0.05. So to determine the probability of having at least 13 or more, we'll calculate 12 or less. Here the function is equals binom.dist. 12 is for x equals 12. N is 125, I've referenced the cell there, and P is 0.05, again referencing the cell. Cumulative is true, since we want all values up through 12. To find the complement, we'd simply take 1 minus the result we just found. So you can see it's pretty low probability of having 13 or more returns.